So, continuing from where I left last time, that is I had stopped at the elliptically polarized light, which and a more generalized case can be, no, the elliptically polarized light is the most generalized case. A little more specific case is the circularly polarized light we saw when the two amplitudes E10 and E20 E10 and E20 become equal. Okay. So, let us go ahead from here. Here I just put in a picture of two polarized light, how that light is, the electric field vector, how it is oscillating. See, the light is travelling like this and at the same time it is oscillating. And if it is right circularly polarized, it will go like this. Okay. So, the black lines there show the electric field, how it is oscillating, and the red line shows the trajectory the tip of that electric field traces. You see this end point here, very light and very faint, it is shown as circle. So, if I take this end tip, if I am able to somehow make a hole in a paper, if I place exactly at some z which is fixed. Here as it is travelling, the z is changing, the time is changing, and when the z is changing, this is what is happening. But if I were to place a paper here, you would see it is a faint circle. This is actually circularly polarized, okay, not elliptically, circularly polarized, because the E20 and E10 are equal. So, you get a circle. Now, this is left circularly, this is right circularly polarized. It is moving in this direction. That is the difference between right circularly polarized and left circularly polarized, which we saw in the equation before. So, the electric field again is moving up and down like this, shown by the black lines, and the trajectory that the tip of E traces goes like this and goes like this. And if I were to put a plain piece of paper at some exact value of z, not exact, some permanent value of z, which is not shifting, then I will get a faint circle here. You can see that faint line here. It traces a circle. Okay. So, the set of points formed by the tip of the vector E lies on a helical line. Okay, this is a helical line. But at one particular z, it will become a circle. Okay, you can follow. Try to imagine that. Imagine what would happen at that plane, that z plane. It will be an xy plane which is perpendicular to the z direction, and what will that tip trace out? It is exactly what this tip traces out, like this, a circle or an ellipse, whatever. In that specific case, it is a circle. This tip will go around like this. If it is like this, it is right circularly. If it is like that, it is left circularly. Okay. That is the whole idea. So, it follows from the principle of superposition. That is what we have been doing till now. We are following the principle of superposition, that any linearly polarized wave can be presented as a sum of two waves with mutually perpendicular planes, okay, of linear polarization. If a phase difference arises between the waves, that is delta, the resultant wave is polarized either elliptically or circularly, depending on the phase difference. Okay. So, there is a phase difference between these two perpendicularly, linearly perpendicularly polarized wave. So, this thing in the green square just sums up all the derivation that we have done previously. Okay. Now, what happens for in the same equation, what happens for cos of delta equal to plus minus 1 and sine of delta is equal to 0. We had taken the other case where cos of delta was 0 and sine of delta was equal to 1. Okay. So, that equation will reduce to just this. Okay. Which equation? This equation. This big equation will reduce to this. When you put cos delta is equal to plus minus 1 and sine delta is equal to 0. Okay. So, this is like a square Ex upon E10 plus minus Ey upon E20 whole square equal to 0. Okay, that is easy to see. For cos delta equal to plus 1, what will happen? Plus, suppose it is plus, you take this minus part of it here. Okay. For cos delta equal to minus 1, it becomes Ey by T0 plus Ey by this is equal to 0. I have just taken that bit in the square, this is equal to 0. Obviously, this square equal to 0 means the one inside is also equal to 0. And this you can see is the equation of a line. This you can see it is a equation of a line. Okay. This is equal to Ex equal to Ey with some constants attached to it. If you take it on this side, Ex equal to V. So, this is the line. Okay. Ex equal to Ey, this is the complete line. And this one traces this line. Okay. When x is positive, y is negative. Okay, so this is the one, y is negative. Okay. When x is positive, y is also positive, then it is this line. Okay. So, it can be this is in this quadrant and this is in this quadrant. They are just equations of line, but only thing the polarization is in a different quadrant, but they are linearly polarized. So, when cos delta equal to plus 1 or cos delta equal to minus 1 and sine delta is equal to 0, you get the special case of linearly polarized light. Special case I say means basically the elliptically polarized light has become linearly polarized. So, here we know now what is linearly polarized light, what is circularly polarized light, and what is elliptically polarized light. They are all basically the same, relating to the electric field associated with that light. But it is, the polarization is a distinct property of that light. Okay, and let us see how we can analyze this. Okay, polarizer and analyzer. So, with what do I analyze this light? How can I make some kind of measurements? Okay, this is happening, but then I should be sure that it is happening. I should be able to make some kind of measurements. So, I make those measurements with a polarizer and analyzer. So, the polarizer is a device that filters unpolarized light so that wave vibration in a specific direction passes through. The resulting light is linearly polarized. Okay. That is what a polarizer is. Now, what is an analyzer? Analyzer is actually another polarizer itself. The polarizer polarizes the light and the analyzer analyzes that light. But as an actual optical element, they are both the same. Okay. So, that is why I say analyzer is a second polarizer used to detect and measure the polarization of light after it has passed through the first polarizer. if the analyzer's axis is parallel to the polarized light, the light's vibration direction, maximum light passes through. Okay. So, what is generally done is like this. So, suppose I have a polarizer here. This is just representative. I have passed an unpolarized light, this I have shown you before, and it passes through, and I am getting in one direction. Okay. Then after that I just place another polarizer, which is exactly this. Basically I have two polarizers with me, and I have this light which is unpolarized. So first I polarize the light, and then I try to see have I really polarized it or not. So these could be, you can get them in two polarizers like this, and the second one you keep rotating it like that, whichever way. And as you rotate it, you will find the light on the other side becomes 0 or 1 or in between. Okay, that is what I am trying to say here. If the analyzer axis is parallel to the polarized light's vibrations direction, then maximum light passes through. Okay. So at one point these two identical polarizers, though I am calling them polarizer and analyzer, these two are exactly in the same position. Okay. When they are exactly in the same position, maximum light will be passed through. If the analyzer axis is perpendicular, then no light passes through. That is when 0 happens. So that is what I am saying, these two here, I am rotating it with respect to each other. So this I am keeping constant, and I rotate this, the second one I rotate. As I start rotating, I will find that the light on this side is diminishing until it becomes 0. So when it becomes 0, that time this is perpendicular with respect to this polarizer. This polarizer is perpendicular with respect to this polarizer, or the analyzer is perpendicular to the direction of the polarizer when the output light is 0. So you can actually see, if it is a visible light, you can actually see it, that the light has become 0. And if it is IR, infrared or UV, there are polarizers, and you have a detector to measure. Okay. Now, if the analyzer axis is perpendicular, then no light passes through. If the analyzer is at an angle theta, the transmitted intensity follows the laws I equal to I0 cos square theta, where I0 is the initial intensity and I is the transmitted intensity. Okay. So what do I mean by that? So now, as I said, that these two, I am slowly rotating the second one. It is not exactly perpendicular to this. That means theta is not pi by 2 as yet. It is an in-between angle between these two, which is theta. Then some light passes through. How much is that light? That is I0 cos square theta. It is given by that. It is called Malu's law. So I0 is the initial intensity and I is the transmitted intensity. So that is how a polarizer and analyzer works. Now we must know how do I make a polarizer? What is a polarizer? So there are quite a few ways of making polarizer. One is they are crystal based polarizers. One is Nicol prism, one is Glan-Taylor prism, and one is Wollaston prism. Okay. All three are just slightly different from each other. Let me describe the Nicol prism to you. So here I have drawn it here. So you can see two triangles, and in between there is a dark blue line. So these two triangles are calcite uniaxial crystals, or they are birefringent crystals. These are two separate crystals made of the same material, calcite, and each of them are uniaxial. That means each of them are birefringent in nature. Try to recall the birefringence that we had studied when we wanted delta n equal to 0. Okay. So in a birefringent crystal, as you remember before, any ray that comes in splits up into the O ray and the E ray, ordinary ray and the extraordinary ray. And if you recollect, I had told you that the ordinary ray and the extraordinary ray are polarized perpendicular to each other. Okay. O and the E ray, they are polarized perpendicular to each other. All right. So now what does this Nicol prism do? How does it polarize? So you have these two rays, and in between these two prisms are stuck together by a glue called Canada balm. CANADABALSAM, Canada balm. So this dark blue line is a glue. Okay. Now what is the importance of this Canada balm? The importance of this is the refractive index of Canada balm, NCB here, as I've written here, is 1.53. Okay. And the refractive index seen by the O ray of this crystal, calcite crystal, is 1.66. And the refractive index seen by the E ray in this calcite crystal is 1.49. Okay. So now when this is split up into two, you look at this O ray. O ray has a refractive index of 1.66, and it encounters a medium with a refractive index of 1.53. So it's a rarer medium, and this undergoes total internal reflection. You remember total internal reflection? If you have light in water, say, and it comes to the edge surface of the water, and the other side is light air, then it gets total internally reflected if it comes at a particular angle. Okay. So that means the other medium is a rarer medium. It has a refractive index less than the one here. The refractive index of this deep blue line is 1.53, which is less than 1.66 of this medium. Okay. So it undergoes total internal reflection. So this angle also has to be in a particular way. So this crystal is cut in a certain way, keeping in mind the uniaxial crystal's optic axis, so that this ray is totally internally reflected. And the E ray, which has a refractive index of 1.49. So this material presents itself to the E ray with a refractive index of 1.49. And 1.49 is less than 1.53. Okay, so this will not get total internal reflection, will not happen for the E ray. It will just pass through. Maybe slightly it will get shifted because there are two refractive indices. Okay, slightly, very, very slightly, because this is a small material, and it will come out. So you physically been able to distinguish between two linearly polarized light. The O ray is one linear polarization which is orthogonal to the E ray. Okay. So you have been able to do that. All right. So you can, so this is a polarized light, this is a polarized light. So, we started off with unpolarized light, and we've got two distinct light fields which have a different polarization. So, that's what Nicol prisms are used for, okay, to make a polarizer. And an analyzer is another polarizer. So, if you use these two together, you can use it as a polarizer and analyzer. What about the Glan-Taylor prism? It's basically the same thing, similar. Basically they call it prism because this is like a prism and this part is also like a prism. So, the Glan-Taylor prism doesn't have a glue in between. Glue of Canada balm is not there. It's just air. It's really precision optics and placing them very nicely together so that you have just air here. And air also has a lesser refractive index as compared to 1.66. So, obviously, this O ray will get deflected. Okay, the similar principle, only in between I have just air instead of Canada balm. So, that is a Glan-Taylor prism. Wollaston prism also has a similar principle. It has some other kind of way of putting these two prisms together. So, these are crystal based polarizers, and they are used very often in optics because they are very reliable and very precise and very reliable, and the loss of light or the loss of intensity is very low in this case. So, these are quite often used in many optical systems, and also because they do not get destroyed easily with high power laser beams. So, they are used in those kind of systems. But then we have some other kind of polarizers also, which are much cheaper than these, but not as long lasting as the crystal based polarizer. Okay. Before I go to the cheaper ones, which is this plastic based polarizers, I will talk about the glass based polarizers. So, even just plain plate of glass can act like a polarizer. It is sometimes called the thin film polarizer. Or remember Brewster angle polarizer. Brewster angle polarizer, when unpolarized light strikes a surface at a particular angle called the Brewster angle theta b, the reflected light is completely polarized. Okay. Tan theta b is equal to N2 by N1. N1 is the refractive index of air and N2 is the refractive index of glass or water. Okay, so this I have introduced to you even before, or you may be just knowing it. So, here this is, if it falls at a this is a glass plate, and this reflected light is completely polarized. So, if it is placed, this glass is placed so that this angle is theta b, then the reflected light is polarized light. And this Brewster angled polarizers or even thin film polarizers are somewhat like this. They are just thin films. They are just plates of glass on which a film is coated. Okay. And it reflects off certain light and it does not. But you have to place it at a particular angle, at certain angle where it will be effective. Quite often these Brewster angled plates are used in the laser oscillator itself. I told you in case of the dye laser how it is used. Why dye laser, carbon dioxide laser or any laser? Suppose this is the cavity. I take carbon dioxide inside. This is like a glass cylinder. Now to this I attach a plate which is at Brewster angle. It is at an angle. Okay. On this side also it is there. So, what is the advantage? What is the advantage of having a Brewster angle plate? The advantage is the light that is coming here, it is at a Brewster angle to the normal to this Brewster plate. This is the Brewster plate. Okay. This is the Brewster plate. They are generally placed this way. So, I get the light that is reflected back, okay, light that is reflected back is totally polarized. And when it comes to this plate, again it is reflected back. It's the same polarization, it goes up and down. Nothing comes out because it gives that angle, it presents that angle theta b. Because it presents that angle theta b to this ray of light which is traveling up and down in the oscillator, the total light will get polarized. And the stimulated emission that is taking place inside, those are also same polarization, because you know stimulated emission follows all the properties of the photon that is stimulating it. Okay. So, it just goes up and down and nothing, there is very little loss here. So, that is the idea of putting a Brewster angle plate. So, what I can see here is that even a Brewster angled plate acts like a polarizer. So, you can have two Brewster angled plates and make it work as a polarizer and analyzer. Then you have the plastic based polarizers. Okay. Those are H sheet, they are called H sheet, they are dichroic polarizers made from PVA films, they are all plastic films. These are quite, they are quite cheap, okay. Stretched plastic with embedded polarizing molecules sometimes. So, they are a whole kind of plastic which are stretched in a particular way in order to allow linearly polarized light to pass through or to be blocked. Okay. You must have heard of, and they are used very often in goggles, in glasses, Polarides and all people call that. Na. So, people wear it in case they are traveling or driving a motorcycle or a car. Why do they wear it? Because they want to cut off the glare. You've heard of glare. Glare happens because of reflection, refraction from different surfaces, metallic surfaces, glass surfaces. So, glare is actually polarized light. So, in order to cut off that glare which is so disturbing to a driver when he is driving, he uses these Polaroid goggles. The goggles are made of these plastic based polarizers. So, it cuts off that glare, it cuts off that polarization. Okay. So, that is how they are used. So, a concept like polarization which seems a bit abstract, but when you are able to measure it with these polarizer and analyzer, you are able to appreciate that property of light.